Good evening to everyone. Today I show you my research topic about flood risk mitigation through smart Levee solution based on fiber optic sensors. And I show you an applied case study in the Emilia-Romagna region. So let's start from the framework in which my PhD research topic is focused. So the new challenges for the hydraulic infrastructures. Nowadays, this kind of infrastructure have to face new serviceability scenarios induced by the effect of the climate change. So, moreover, we have a need of integration of innovative and competitive monitoring solution as those proposed by fiber optic sensors with the existing and installed ones. And we need an improvement also of the maintenance procedures because we are facing an increasing age heritage, infrastructural heritage. So in Italy, more than 80% of the dams, for instance, were built before 1960. And last but not least, we have the support of AI and big data contribution for manage the safety and control, so understand the potentialities and the limits of these new technologies. So the goal of my research is the conceptualization of monitoring solution based on fiber optic sensors when they are installed within complex measurement systems. What are fiber optic sensors? Fiber optic sensors are optic sensors based on fiber optic cables. So the typical standard fiber optic cables that provide us a fast internet connection in our houses. And they are basically composed of an inner core that can be made of glass or plastic and an outer cover coating that can be armored or unarmored depending on the installation and the context in which these sensors are fixed and installed. These kind of sensors, so fiber optic sensors, are used to measure mainly strain, temperature, and pressure. Here we have a typical layout of a monitoring system based on this technology. So we have the sensing loop, the fiber optic sensor loop that is installed fixed. Il mio è staccato. Riesce a venire qua? Ma interrompi, si esce. Ci sentite da casa?
Non sono a casa, ma sì, vi sento.
Ok, perfetto. Grazie. La schermata è rimasta. Questa no.
No, quando vedi l'intero schermo.
Questa qua. Okay, so let's go back to this slide. So this is a typical layout for a fiber optic monitoring system. We have the sensing part is in some way fixed, bonded to the structure, and this is a crucial issue in choosing what is the best solution to guarantee the correct transfer of the parameter that you want to measure. Then we have the leading cable that can be extended up to 2, 3, 4 kilometers length. And this cable transmits only the optical signal and the data. And then we have the interrogator device that can be placed remotely. And depending on the technology on which it's based, fiber optic sensor can be fully distributed, quasi-distributed, such as in back gratings, or integral in as regards the spatial dimension. Among the distributed fiber optic sensor, those based on stimulated brilliant scattering, so the brilliant technology can measure strain and temperature variation with high accuracy. We talk about alpha degree and 10 microstrain for mechanical strain measurements. And an important aspect is that in brilliant frequency shift, so the raw data is a frequency because we are dealing with the optoelectronic world. The brilliant frequency shift is the linear superposition of the temperature variation and mechanical strains. And there are several technologies and solutions to split these two contributions that have a very large history in literature. Why fiber optic sensor? We have a very long list of advantages. Here I reported some of them. And we have, first of all, the great adaptability to each kind of infrastructure due to its nature of linear sensor. So it well suits with the linear characteristic of infrastructure. Then we have an high resistance to harsh environments and in particular the immunity to electromagnetic interference. This is a very important feature when you have to install a monitoring system in a very complex and logistic environment. Then we have the absence of power supply. No power supply is needed for the sensing infrastructure, but only the interrogator device that can be installed remotely. We talk about 2, 3, 4 kilometers if we talk about the brilliant technology. And last but not least, we have this increased competitive cost. The fiber optic sensor, those that are commonly applied for internet connection, cost about 10 cents per meter, whereas as regards the very important parts of the interrogator device, we also take into account that nowadays their cost is about 1/10 with respect to 10, 15 years ago. So let's go deeper in my research method. We have these two important activities that are experimental test and physical numerical modeling. These two activities are performed simultaneously in order to get the correct definition of the fiber optic sensor monitoring solution. So we have to select the type, the cable type, the interrogation technology. We have to choose the best bonding solution. It's a very important part. And in the end, we have to validate the sensor layout by comparing the results of the physical numerical modality, so the famous digital twin, with respect to experimental evidence. And now, this is the ongoing part of my work. That is, okay, we have this new monitoring solution. We have to integrate it with the existing framework, so to the existing sensor network or other environmental measurements observation that can be provided in the same location in which the infrastructure is placed. So by the using of physics-informed machine learning, we want to get to an interpretation model that can learn by the stream of observation data, but obeying also two physical laws. So finally, we reached this enhanced digital twin, getting the hidden knowledge, the knowledge hidden in this famous big data. And this tool can provide insights and decision support by monitoring and predictions. These are the main case studies of my PhD work. So the first one that I started 3 years ago is this water pesto bridge in the upper part of the Valle d'Aosta region. Then we have the latest case studies that are this map pipe. So we verify the possibility to use this distributed fiber optic sensor for monitoring pipeline made of high-density polyethylene. And then the last one that I will show you this evening is the smart Levee that we installed in Modena. So let's talk about this project. The project has been financed by the Agenzia per la Sicurezza Territoriale e la Protezione Civile della Regione Emilia-Romagna, and the main partners we have the Fondazione Politecnico, each of the partner of the University of Padua, and then the two industrial partners that are Officina Macaferri and Optosensing for the optoelectronic component. The concept is based on the integration, the coupling of a geomat reinforced with wire mesh, reinforced double twist wire mesh, and covered by this layer. This is an extruded propylene that offer a layout for the growing of the grass turf, superficial grass turf. And then the sensoristic part is the fiber optic sensor. In this case, we have a polymeric optical fiber that presents some advantages with respect to the glass ones, because we have a very high flexibility and a very high resistance when it is placed in an external environment or in a position where there are strong solicitations that can mining the integrity of the line. And our task is to create a geomat, so an anti-erosion revetment that for the structural component, it prevents from the soil erosion and the activity of the burrowing animals. And from the sensoristic part, we have a real-time monitoring of the functionality of the levee, and it offers a tool for civil protection decision support during flood events. So we have a permanent sentinel on the river that provides continuous data about the integrity of the levee. This is the layout that we perform on the site. So we keep each roll, we install 4 rolls of this geomat. We keep them with these 2 sensing loops made of polymeric optical fiber, and each line is interrogated by this integral interrogator device. So each panel of revetment is equipped with all the technology needed for reading integral strain and temperature in terms of optical strain attenuation. So here we don't have, like in distributed fiber optic sensor, a strictly correspondence relation with the physical world of microstrain and degrees, but it is in terms of optical signal attenuation. And each panel, so each fiber loop is interrogated by its own devices, and so all the technology is mounted on this revetment, smart revetment. How to? We first performed this last test on the bonding solution, the best bonding solution, because we have to verify what is the best solution for the coupling in order to have a correct transfer of the strain and variation also of the mechanical behavior of the wire mesh. Here you can see the one of these experiments in which we take a sample of this geomat, a square sample, and we attach to these 3 steel frame, and by exerting in-plane loads, so by stretching this sample, we verify that the optical fiber can detect properly the linear behavior in the formation of this structure, of this element. The linear behavior was verified, was learned during my first master thesis, and so we took this knowledge and we verified that the sensor can properly detect, transmit, and read this linear behavior by applying a load cycle. Then we have so the experimental part, as I said before, and the numerical modeling part, my work. So we design the digital twin of the prototype of this smart revetment on SAP by using finite element modeling, and starting from the digital twin, we investigate the behavior, the mechanical behavior, and so what the fiber optic sensor would read when a given displacement, a local given displacement is induced in order to simulate the local slope failure of a given embankment. And what about the applied part of this solution? So we managed to put these smart revetments along the most critical river section, as those in urban areas, for instance. So we don't imagine to cover all the embankments of all the rivers with these solutions, but we want to put a permanent sentinel, as I said before, in the most critical parts of the river in order to have a constant and real-time monitoring of this critical section. Let's talk about the test site. The test site is placed in Fossalta by the town of Modena in the Emilia-Romagna region, and we are in a very critical hydraulic node of the Po plain, in the sense that here we have the Panaro River and these two minor creeks that are Tiepido and Grizzara Creek. The important issue in this place is that it suffers from the backward water from Panaro during flood events, and in several cases, in several dates in the time, the area was heavily flooded, and this is a very important area for the urban area of the economy of Modena, because we have a lot of companies, a lot of industrial and commercial activities, and also residential ones. So the first image referred to the last flood, the last very important flood of December 2020, whereas in the lower part we have the result of the flood of May 2023. After that, the Agencia, the Civil Protection Agency, performed these important restoration works of the River Tiepido embankments and other hydraulic works in order to guarantee the hydraulic safety of the area. So, what about the test site? We installed about 200 square meters of smart revetment, both riverside and landside, by coupling, as I said, fiber optic sensor and MAC geomat. And we also installed a sensor network for soil temperature and water content measurements in order to have a clear knowledge of the mechanical behavior of this levee, thanks also to the support provided by the University of Padua. And with Padua, so we implemented this system, solicitation system on site, made with these lifting bags that are buried landside under the smart revetments, and all the systems, so all the sensor, the network can be remotely tunable as regards the acquisition rate. So let's see the phase that brought us to the realization of this smart levee. We have the superficial digging of the soil to break up the existing turf. So we have to break the existing turf. Then we perform the installing of the sensor network, the other sensor that I mentioned before. And last but not least, we have the implementing of this system. You can see here one of the 4 lifting back that we have to test next weeks. Then we have the second phase with the sensory revetment assembly that we perform in Reggio Emilia in this factory. And in this case, we perform the hand bonding of this loop of fiber optic sensor on 4 rows of reinforced geomat. Overall, we install about 400 meters of fiber optic sensor on about 3,000 portion of bonded portion along all the geomats. And after each installation, we also perform this checkout testing on each revetter in order to ensure that it works properly. This is one of the results of this testing, in which we stretch all the panel by anchoring it on the floor. And we can see that with a given displacement, usually by stretching on the other side with this rope, and with this control rod we apply a given displacement up to 7 centimeters, and on the other part we have the optical signal amplitude that decreases accordingly with the displacement induced. This is the third part, part of the installation. So we have the laying, the anchoring of these 4 rods along the river. And the shear is quite slow. The covering with 10 centimeters of topsoil in order to create a layer for the new grass turf and the assessment of this new topsoil. And then finally we have the hydro seeding of the new grass turf in both sides in order to complete the work and to recover the original condition of the levee when we start the test site. Okay. What next? What happened? So after 3 weeks from the completion of the works, the Emilia-Romagna region was hit by these 2 strong events. These 2 flood events that hit in particular the Romagna part of the region. In particular, during the second one, intense rainfall exceeding in most of the Romagna River Basin the 200 years return period, as if we talk about the 24 hours rainfall duration. Our test site is placed in the tag, yellowish tag, and unfortunately there were no floods exceeding the levee crown, but all the water table was contained by the new levees. And this is the outcome from this is the outcome from the fiber optic sensor placed riverside. So you can see here the cross section that we just taken but a topographic survey. And we have these 2 sensors, F5 and F8, that are placed on the upper and the lower part of the levee embankment. And so this is the linear response in terms of optical attenuation. Whereas in the right axis, we have the water level recorded at the hydrometer placed at Fossata Bridge that is very near our test site. So we can show how the flood wave in both cases is well recorded in terms of optical attenuation by these sensors, and we can see also the uprising of the level, because we have the first decrease in attenuation in the F8, and then we have slightly mismatch with respect in time for F5, and we have the recover. Another important thing is that during dry season, so during when we don't have precipitation, all the system can detect properly the daily temperature excursion of the wire mesh that is inserted that is covered by the soil. And when we have an event, this response is stopped in some sense, because the prevailing one is that given by the uprising level of the river. So they are the very first result, and an important thing is that we talk about optical attenuation. We don't have in literature a straight correlation between this optical attenuation and some mechanical strain or temperature variation. In this first part, we start with this analysis in terms of Spearman correlation coefficient between the fiber optic loops that I saw before and the temperature variation. And we can see, as I showed you before, that we have a very important negative, we have an important anti-correlation, so between the variation of temperature and the attenuation. And this is a first result in the sense that we want to perform a model that is able to interpret this data. How? We have to build this famous machine learning layer. So each event marks the system response with its signature. So we have the thermal excursion during the dry period, then we have the wet periods, then we have operation for cutting grass and whatsoever. And the response of the system in terms of optical attenuation is marked by these events. So by using supervised classification, we want to learn the evidence. We want to learn by the evidence how to recognize a status that is complied with a given solicitation. Okay, and what about new experience system status? So a new version, a new status that was never experienced before. Well, after a proper classification, this can be inserted in the historical framework, and historical experience, evidence of the system, and can be tagged as a warning status or not warning status. So by this classification, this never experienced status can be can come from the evidence, the observation evidence, or by a synthetic simulation of them. And then lastly, we can implement our early warning system that can be activated when specific status occurs. So this is the ongoing part of my work. So to conclude, we consider the first prototype of this smart development, and the outcomes coming from the first 8 months of testing, on-site testing, are promising in terms of resistance and sensitivity of this solution. Data interpretation is ongoing, as well as the development of a machine learning layer. And the next weeks, we had some problem with the solar power system, so we have to postpone this phase. So in next week's solicitation or test with barring little bag will be performed on site in order to enhance the knowledge about the response of this system. Thank you.